Now, before we move on, I need to tell you what chemical potentials are. So very briefly, what is a chemical potential? We defined chemical potential as negative T partial S over partial N mu and V. And we introduced a negative sign in here. Now, negative sign in here implies that the system with larger mu S over N will get more particles. In fact, what it means is that the particles will flow from a higher mu over T to a lower mu over T. So at diffusive equilibrium, the conditions that must exist at diffusive equilibrium, the conditions that must exist are TA must equal TB, PA must equal PB, and mu A must equal mu B. And the negative sign implies that the system with the larger partial S over partial N will get more particles. In other words, what this is saying is that particles will flow from high mu over T to low mu over T. And chemical potentials play a vital role in many parts of thermodynamics, which include processes like melting, boiling, evaporating, osmosis, and many more. Is vital in our understanding of many thermodynamical processes. For example, boiling, evaporation, osmosis, etc. Now, what is the physical meaning of chemical potential? So when two systems with different chemical potentials are brought into chemical contact with each other, particles will move from a system at higher chemical potential to the system at lower chemical potential until they both reach chemical equilibrium. Now, suppose you have two containers of gas that make up systems A and system B at different chemical potential. Also suppose that system A is at a higher chemical potential with respect to system B. So when you put them together and you allow them to exchange particles, say, for example, if there was a valve between them, you open the valve, there will be a net exchange of particles until both reach the same chemical potential. So what we're saying is that under most conditions, chemical potential will determine the stability of substances and also their tendency to react to form new substances. So in that sense, it is a central concept in thermodynamics of materials because all of the thermodynamical properties of a substance may be obtained if we just know the chemical potential of the substances. So let's write that down. Suppose you have two systems. A and B. System A is at chemical potential UA and system B is at chemical potential UB. Suppose UA is bigger than UB, and when they are brought into chemical equilibrium with each other, particles will flow from UA to UB until they both reach chemical equilibrium. So we can say that in most circumstances, mu determines the stability of the substance and its tendency to chemically react to form new substances. So put this in a box and make sure you understand that it's important. So this is the reason why it is so important in chemical thermodynamics, because once we know the mu, we can find all the thermodynamical properties of the substance. Now, before I move on, I want to make sure that we understand this. It's important to note that high chemical potential is not always caused by how rich a substance is, basically how many number of particles it has. It is also caused by how generous a substance is. In other words, low chemical potential is not always because the substance is poor or it has lower number of particles, but it's also that it's not willing to give up these particles. So think about a miserly person versus a very generous person. So a person who is rich and miserly will tend not to give up his or her money, will tend to hoard the money and will want to attain more money. Whereas a person who is generous, even when they have little money, they are still willing to give up their particles. So a rich, miserly person might be lacking in generosity, or in other words, have lower chemical potential. But a generous person, even when they are not rich, may actually have higher chemical potential. So this I've shown with a very good example. So a poor, generous person will have a higher chemical potential than a rich, miserly person. So there are some examples given in the book that include humidity, the pH balance, the Nest potential, and for the ideal gas. For our case, the one for the ideal gas is the most important. So the example that I want to focus on today is the chemical potential of an ideal gas. Mu at Tp at Tp0 will actually be given by Kt log of the P of the gas divided by B2. Note, P0 is usually taken as 1 atmospheric pressure. Other examples may include things like humidity, where humidity is the tendency of an atmosphere to give water molecules, hence the chemical potential of water molecules. of an atmosphere to give water. So in this case, mu of water minus mu zero of water equals RT log of P water divided by P zero. For Nernst potential, Nernst potential is a tendency of the system to take electrons. So tendency of a system to take electrons, and the pH is the tendency of a system to take H ions. So the chemical potential of a proton is given by divided by RT log of 10.